All right, I think we left off around here. This may be reviewing just a little bit, but I want to make sure we cover all this stuff. So when talking about trying to capture sort of latent, variables, things we can't directly measure, one of the issues that comes up is that oftentimes these variables are complex. So tests that we use to measure a concept or construct typically have a moderately large number of items. So this, you can think of this as sort of based around sort of domain sampling. We tend, because more items are better under the domain sampling sort of theory, we tend to have a lot of them, right? So they tend to be, 20, 30, 40, 50, tend to be lots of items. You got the MMPI, it has like over 300 items, right? So with this comes a whole mess of relationships, lots and lots of covariances, lots of correlations. And if we use something like alpha, Chromebox alpha, to look at the internal consistency of those items, well, that starts to become problematic because there's a couple issues. One, if we assume that there's just one general pattern across all these large number of items, we can use Chromebox alpha, but it's likely not to fare very well. Especially in cases where you have, sometimes we like to reverse coded items where, questions asking about anxiety, or let's say it's depression. You might have a question that's like, oh, I feel happy all the time, or I rarely get sad. Those kinds of questions that are sort of in the reverse direction, just to keep people from responding in some sort of lazy way, or they just sort of circle all the fives or something. So sometimes we'll reverse items to make sure that everyone's sort of really reading and answering the questions. If you leave those questions reversed, that ends up leading to a negative covariance. And when you add those covariances up for Chromebox alpha, those negative covariances are actually going to hurt the overall alpha value. So all of them have to be reversed first, and it's a whole process to make sure they're all in the same direction. So think about something like this. I think we looked at this last time, but this is the correlation matrix for the math anxiety scale. It's a ton. It's like 24 items by 24 items. It's lots and lots of correlations, right? So for us to be able to pick out the patterns of correlations or covariances or something to test through a Chromebox alpha becomes complicated very fast. So and to try to think that there's just one pattern that explains all these correlations also becomes pretty unlikely. So Chromebox alpha starts to sort of fall apart when it comes to having large numbers of items, especially if there are multiple threads, like subscales, things that are actually being measured. There are slightly nuanced differences between things. You see this in I pick on depression a lot just because it's a sort of familiar sort of topic, but in depression there's things about sort of changes in mood, there's changes in weight or energy, there's changes in sleep, there's a factor in there called anhedonia, which is where you lose the joy, you don't enjoy things as much as you used to. So there's all these different sort of subtypes, factors of depression that if you're using something like a Chromebox alpha would not be captured in this, right? We're not be able to see that. So alpha can give a single value that illustrates an overall relationship, but it's just looking for one consistent pattern. If we can measure the concept directly, we could do this differently, reduce the entire matrix on our previous page down to a single value as well, if we wanted to look at something like a multiple correlation. So remembering with regression, that if we have a single outcome y, we can predict it with the number of x's, and then we'd have an intercept, some error, which is just the difference between the actual value and the predicted value. And lots of slopes, we can do that. And we end up having a y predicted value, where the y predicted is the value on the line, and the y value is the actual score. So that the difference between these two things, as you can see in the equation, is e. All right, so e, our residual, is just the difference between each score and the predicted score. Which looks like this, right? So here's our y predicted along this red prediction line. And if this is a country's actual score here, and this is the predicted score, the difference there is the residual. So we can look at the residual as just the difference between what we predict for an outcome and the actual outcome. It's just the residual. Okay. So that means that y hat is the part of y that is related to all the x's combined. You look at so this y hat is the part of all these x's, right? It's the part of y that all these x's relate to, because the part that the x's do not relate to is found in E. Okay, that's the residual. So we can find a multiple correlation by combining those x's together into a y predicted, like this here, and correlating that with the original y. The higher this correlation is, the larger the multiple correlation, the larger that all these x's are capturing y. So I can look at multiple correlation, which would give me a sort of a general pattern of how all the x's all relate to a single outcome, if we had that outcome, right? If we actually had a y, like if we actually had a measure of depression, something concrete like a clinical interview, I can take the items on my scale and I can correlate them to that y and see how well they relate. This is sort of like a reliability. It's just looking at reliability of all the items sort of combined in sort of a smart way. So usually we typically add them all up to create a composite and correlate that to another outcome for reliability. This would at least give us some measure of weights, so we can tell which x's are better or worse at capturing y, and we can actually get an overall measure which would give me something like a reliability. But the problem is, this is using a clinical interview for y, so we still have to have some concrete outcome. We can even square the value of that multiple correlation. We get something called the squared multiple correlation, oftentimes referred to as the SMC, which will tell us the proportion of y that those x's are capturing. So importantly, if y is the constant criterion we were trying to measure, and the x's are items of a test, this would give us a single measure of how well those items are capturing the concept. But again, you still have to have that concrete outcome, something to predict, clinical interview, some criterion which will allow us to do that. So what to do? Well, it's the same problem. If we can't measure the concept directly, we can't apply a regression equation, right? We can use some other proxy, but then we're trying to create a proxy scale, some measure, and then using some other proxy to sort of guide our choices about the quality of our scale. So it's still sort of problematic. So if we can't measure the concept directly, we can't apply the regression equation, we can't establish optimal weights for adding items up, and we can't reduce the number of patterns. We can't, using something like R, we can't do that unless we have some kind of outcome. So if only there was a way to handle this. So what would we do? Well, we're going to rely on some fancy mathematics. We're going to rely on a bit of geometry and some other things that are going to happen in the background. We're not going to go too much into the details of those, but the things that sort of occur in the background that allow us to identify patterns and relate our items to those things so that we can actually look at the relative importance of items when looking at different factors. Okay? So what is factor analysis? So factor analysis and principal components analysis, those two things will at times, you'll see them used interchangeably. They're both essentially doing the same thing. They both rely on the same sort of initial process. This idea of identifying patterns in a correlation matrix are done by both of them. It's just the way in which they do it is a little different. PCA tends to be a little more simplistic, and it's done a little bit more at the beginning of research process when maybe the relationships among items are not as well known. Factor analysis is done when there's a little bit more theory behind sort of driving the questions, and it's a little bit more mathematically complex. Not just complex, but a little more mathematically like mature. It does more to try to get at the real relationships between variables and and one another than principal components does. It sort of digs in a little bit deeper. So they're both methods of data reduction. They both are used to apply to a correlation and try to break it down into smaller chunks. They take many variables and explain them with a few factors or components, depending on which one you're using. Correlated, and the process here is they try to find variables that go together that are correlated, and they try to group them. They try to find a pattern of groups of variables. Let's put those together and we separate them from other groups of variables and put those together and try to separate them out and try to find different patterns. So they both do this, they just do it a slightly different way. So variables with low or no correlation are sort of separated. Variables with patterns of correlations that are sort of similar and that sort of relate are sort of grouped together. And the difference between here, this is, you may be thinking this sounds a little bit like cluster analysis or something. You've heard about that, where with cluster analysis the goal is to try to group together people, respondents, individuals, things that you're measuring, the actual targets. It's using a very similar approach. It's trying to find patterns of responders to sort of group together. That's sort of cluster analysis, where factor analysis, PCA, are trying to find groups of items, of test items that are similar and group those together to represent factors instead of clusters. Clusters are people, factors are groups of items that go together. So what is factor analysis in general? So patterns are identified and either used as sort of descriptive and a means of sort of making composites, or they are indicative of some underlying theory. And it depends a little bit on what you're trying to do. If it's truly just data reduction, PCA is fine. If you're trying to uncover what the underlying sort of motivation is behind the people's responses to items, then it's really more about factor analysis and trying to sort of get in there and look at those things. It's a process. This is also the important thing here. This is where it really comes back to this idea of measurement. It's a process of providing an operational definition for latent constructs, right? So through these regression-like equations. So we want to measure depression, right? So depression's a complicated, multi faceted thing that we're trying to measure. It's this metaphysical sort of, you can't directly measure it. So we need to operationally define it some way. Now, you can do a super simple operational definition like I feel depressed on a scale of 1 to 10. And you can use it as your operation, but it doesn't really get at the sort of nuances, the subtle differences between different expressions of depression. And so what factor analysis and PCA will do is allow you to have a more complex, nuanced approach to identifying or operationally defining a variable like depression that includes all those different sort of aspects all together. And someone could be high on depression for different reasons that other people are high on depression, and it allows for a sort of multifaceted, more complex, more inclusive way of looking at it. So it's a much more nuanced operational definition than just having a single item where you ask someone to rate the depression on a scale of 1 to 10 or something. And that also requires that someone is aware that they are depressed in order to sort of answer it, whereas sometimes you can build in questions that are much more subtle into a factor analysis. So someone responds to those, they may actually end up being more depressed than they even realize because of the types of questions and the subtlety with which the items are created. Okay. So in general, there are lots of different types or approaches to factor analysis, and some people may disagree with the way I'm sort of organizing this, but I see principal components analysis as just a type of factor analysis, right? It's the same approach. When people say factor analysis, oftentimes you'll I factor analyze these data, and you go and look, and they actually did a principal components analysis. So I think people in general have this idea that the principal components is a type of, or at least interchangeable with, factor analysis. It is a much sort of simpler sort of approach. It has some sort of different assumptions between principal components and common factor analysis that we'll talk about shortly. But the idea is that there's principal components analysis is this sort of descriptive process of how to reduce data. And then there's common factor analysis that's really looking for common variance and trying to identify the underlying sort of reason why people respond in a similar way to multiple items. And even that can be broken down further. There's what we're generally talking about in this sort of lecture is something called exploratory factor analysis, which in lots of ways is exploratory. And I think people actually use it in ways that really aren't exploratory. Like there are people that really have an idea. They really have expectations about their data and how their data is going to group together. And yet they do exploratory. I think more or less that's just what they know, what they're familiar with. So you see a lot of exploratory processes in and factor analysis that are done, and it seems strange. Like, well, okay, well, you knew you're going to get 4 factors, you knew which items go where. Why are you exploring? When really they could have been doing confirmatory factor analysis, which is more it's more computationally, it's sort of intense. It relies on things like maximum likelihood estimation, and it requires a lot more sort of computational power. If you're running this through a computer, through computer software. Exploratory factor analysis has been done for a long time, decades through computers. Where confirmatory factor analysis is becoming a lot more readily available, especially in the last few decades, because of computing power becoming faster and faster. But it really relied on there to be some computational speed for computers to be able to do this in a way that made some sense. I mean, we went from even exploratory factor analysis. You go far back enough, you used to have to wait for your computer to run these things. It would take the computer a long time to do them. I can remember running a confirmatory factor analysis or something like that, and having to run it and then go do something else for a while, like leave and go to lunch for a couple hours, so that when I came back, maybe it was done. And even in other cases, sometimes you'll see that go back far enough that it may have taken days, for some of the stuff to run. So it really had to do with sort of the computational power of computers to allow us to sort of move to a more, computationally intensive approach like confirmatory factor analysis. Which is why I think that people oftentimes will do exploratory when they really should do confirmatory. I think it's a lot of it that they haven't quite got to the point where they're as comfortable or used to confirmatory models. But I mean, that's changing. I like to be optimistic. I think more and more people are sort of moving in that direction. So general steps to doing a factor analysis. These are the same steps, again, to any kind of factor analysis in general. So that you're talking about principal components analysis as well. You're going to select and measure a set of items. So you got to have some kind of domain you're interested in. You got to have items that are measuring that domain. So if it's, again, like depression, you're going to have depression items that you're going to try to to factor analyze, and you want to know if you've made a good operational definition of depression using these items. You're going to do some data screening in order to prepare the correlation matrix, and that's just a fancy way of saying, look, you need to go through and look for things like outliers and skewness, because anything that would affect the correlations, that would make the correlations bigger or smaller than they really should be, are in turn going to affect the factor analysis. So there needs to be some data screening done. Make sure that you've looked for people inputting the wrong numbers or mistakes in data entry, super crazy extreme scores, stuff like that. And once you have that, you're going to then go to the point of factor extraction. Now, factor extraction sounds crazy. When you extract factors, it's really a process we'll get to shortly, that we are applying this sort of mathematical process, this process of trying to identify patterns. That's the sort of factor extraction process, and it has a couple different components to it. It's like some assumptions or beliefs about the data, how you want to actually extract, and then also the number of factors you want to extract are all sort of part of that process. Once you've extracted factors, you decided on the number of factors, the way you want to extract them, all these different decisions about extraction. Now you have factors, but sometimes those factors are not going to be easy to interpret because of the way the factors get extracted, the way they get identified. It's done through a sort of geometric process. So sometimes it's not optimal. Sometimes it could be optimized somewhat to make it a little easier to understand, and that's what factor rotation does. Factor rotation allows the factors to sort of rotate in space. And I think this is getting a little bit out there theoretically, but it allows them to move in space in such a way that it helps to increase the interpretability of the items and factors. So you can understand why certain items are going together. You can figure out what what these factors are sort of identifying, what different, like if you think about depression, what different subcomponents of depression are being identified by these items. That's what a rotation allows you to do. It allows you to sort of optimize. So it's really about sort of, let's identify the factors and sort of extract them, and then let's try to optimize them in a way to make them a little bit more interpretable. So once you've done that, you sort of maximize the interpretability. Well, now you need to go about interpreting. You need to actually go through the interpretation process. Even though this is the stuff up here requires the sort of mathematics and is the sort of intensive statistical components, sometimes the interpretation is actually the most difficult part, because now you have to look at items. You got to look at what the items are asking, what the content of the items are, and try to figure out, well, why would these items sort of go together? What would be driving these particular items to be similar, or to share variation? And sometimes it's not super clear. Sometimes it can be really difficult to figure out why items are sort of consistent with one another in a way that seems surprising. So interpretation can be hard, and I've said this in other places, and I'll repeat it again, that the factor analysis is a mixture sort of art and science. You got the science part, you got the extraction, this sort of geometric approach to trying to identify factors, this is mathematics and stuff, and the rotation. But then there's a lot of subjectivity and a lot of sort of practice and other things, and just an art that goes into interpreting and understanding the factors that you've identified and extracted. So it does take practice, and it's almost it's impossible probably to ever just do a factor analysis through one time. You're going to end up doing it and then redoing it in different ways with different options to try to figure out which one actually seems to work the best and gives you the sort of best interpretation. So sometimes if you do a factor analysis one time through and it's not easy to interpret, you may need to try different choices to factor analyze your data to improve that interpretation. And once you've sort of identified the factors and you've sort of figured this stuff out, well, it's now time for further sort of validation. Do the factors that you've identified during this process, do they correlate with other factors of the same thing? So looking at sort of content-related evidence for validity, or if you're doing a depression inventory, do the scales relate to a clinical interview to do sort of criterion-related validity? We can apply things like Chromebox Alpha to the items on a factor to see the internal consistency of those items. We can then do retest reliability of the questions to see if we're able to sort of capture the same factors again and see if they're reliable. So there's just more work to be done. And oftentimes more data to be collected and more factor analyses to do to finally get to a point where you really understand how the items are working and what factors are really driving those responses. Okay. So factor analysis questions. 3 general goals. Okay, we have 3 general goals, and this is true of factor analysis and principal components. Okay, we want to reduce data down. So you have a 24 by 24 matrix. It's pretty hard to do anything with that. I mean, that's why oftentimes the easy route is just to add up all the items and create a composite, because now you have at least all those items have been sort of compacted into a single measure, and that's much easier to predict or use as a predictor in regression or something like that. So when you have 24 items, trying to figure out what to do with them is hard. So we want to figure out a way to reduce them and try to find patterns where items can be combined together in a smart, effective way. Can really reduce things down and make them more useful. So again, we want to increase the interpretability and the usefulness, the utility of items. So data reduction is a nice useful thing to do. So let's actually make it these huge numbers of items into a smaller number of usable factors. That's awesome. It's again when thinking about operational definitions, we also want to be able to describe relationships. Operationally define factors or constructs that we were trying to measure by trying to describe the relationships between items being driven by those concepts. That actually is a very useful process too. And if you also have theories about how items are related, then you can also test those theories as well, and things like confirmatory factor analysis, where it says next chapter, which is referring to item response theory that we're not going to cover, but in a longer semester-long course, I'd likely would take some time to talk about item response theory too. So you get, how many interpretable factors exist in the data. That's sort of this data reduction and identification process. How many factors are needed to summarize a pattern of correlations? So you have a bunch of correlations, and how many factors are needed to really summarize them, but still be able to capture those correlations, to be able to capture all the relationships between the items with few factors. What does each factor mean? How do you interpret it? How can you actually look at that and actually interpret the factor in some way? And then what is the percentage of variance in the data accounted for by the factors? Are the factors actually accounting for a large amount of the variance in the items? Because if they're not doing a very good job of covering the variation in those items. So it's important that the factors actually do a good job in explaining the variance in those factors. So if the factors are accounting for the variance in the items, well, which factors account for the most variance? Are there some factors doing a better job than others? How well does the factor structure fit a given theory? So you have a theory about how the items are supposed to be related, and what's supposed to be driving the items. Well, did you actually find that? Did you actually confirm the theory that you were trying to test in the first place? And then this one's actually an interesting one too, since we're trying to operationally define a variable that isn't easy to operationally define. Once we do that and we find sort of factors that seem to work and that we can interpret, well, what would the subject score be if they could be measured directly on the factor? So again, if you're trying to do something like a depression inventory, and you factor analyze it, and you come down to these sort of sub-factors. Let's say it's anhedonia or something like that, which I just love saying. It's a fun word, which means sort of the opposite of hedonism. So it's like the lack of pleasure, lack of fun. If you're trying to, if you find a factor and a bunch of items that look like they're about losing interest, losing fun in things you used to find interesting and fun, and you have a sort of an anhedonia factor. Well, I don't want multiple items. I have these sort of these weights and things, these regression-like slopes that I can use to then combine those items together into a single factor score that I can then use as a variable. So these are sort of smart composites. They're not just composites where you add the items up, but you're differentially weighting the items so that some items are used more and some other items are used less, depending on their relative importance to that factor. So we can actually estimate, or at least calculate, a value for what the person might have scored if you're able to measure them directly on that sub-factor. So that's pretty cool too. Types of factor analysis. I mentioned this before. You have the exploratory factor analysis, which we're able to sort of summarize data by grouping correlated variables together. It's purely mathematically driven. We're going to allow this geometric process to go through and find the patterns for us, right? So it's mathematically driven in that way. So it's going to explore for us what the patterns look like and where they might be. So it's investigating sets of measured variables related to theoretical constructs. It's usually done at the onset of research, even though people, again, continue to use it well past that point because it's what they're used to. And it's the sort of type we're talking about in here. We're not going to get into confirmatory factor analysis in here. Again, it takes us into a different course altogether. So we're sort of going to focus on talking about the basics of exploratory factor analysis. Confirmatory factor analysis, like I mentioned before, is a more advanced technique. It's when the factor structure is known, or at least you have a theory about it, or you've done a exploratory factor analysis. Now you want to know if that generalizes to other data. You can actually directly test it and confirm it in new data. All right, so this is often tested through approaches like structural equation modeling, simultaneous equations. Sometimes people call them LISRO models or something, but it's done in a more sophisticated way because it requires maximum likelihood and other processes that take it beyond the typical like least squares or ordinary least square sort of approaches or stuff that goes along with a lot of stuff we talked about so far. All right, so this is sort of beyond this course, and if you're interested in something like this, find like a class on latent variable modeling or something like that. It'll sort of take you beyond exploratory to more confirmatory models. Okay? So remembering CTT. So one of the things that I tried to do with this lecture the first time I put it together was I was trying to explain factor analysis in a way that, one, required very little math. I was trying to stay away from mathematics, and because I was teaching this to an undergrad course, and I knew a lot of students wouldn't have enough background to be able to talk about some of the things that go on in the sort of mathematics of factor analysis and things. And because of that, I sort of taking the sort of mathematics away, I wanted to focus on sort of conceptual understanding. So if we assume, all right, so let's go back to the sort of true score model, and we'll just try and connect this together to sort of how factor analysis is working. So CTT assumes that every person has a true score on an item or a scale if we can only measure directly without error, right? So everyone has a true score, but what we get is the true score plus some noise that happens whenever we're measuring anything. There's measurement error. So we end up having our score that's a mixture of sort of true score and error. This is assumed for every person. It's assumed that there is everyone has a true score for something, and what we get is a mixture of that true score plus some noise. Okay. This is that sort of common true score model. So let's think about this as an item. So this is, if this were a particular item on a scale, we could think about it, take it a little bit farther, where we have an item on a scale. Everybody has a true score on that item, plus some error variance on that item, some error, random noise around the item. And if we actually look at this as across multiple respondents, look at a data set of everyone responding to the same items, we can think, all right, that means that the variability, the variance across people for that item K on this X scale, okay, this item has a certain variance. There's some portion of that variance that's being driven by their true score, because people are just differ on their true score, so there's going to be some variability on their true score. So part of this is going to be variability that's being driven by just real differences between people's scores. But then there's also going to be noise added in, so there's some variability between people's scores that it's just error, just random noise. So we can think of this in terms of variance as the variance of this item is a combination of the variance related to the true score and the variance that's related to sort of measurement error or noise. All right. Since we don't know T, we don't know it at all, it's hard to sort of identify it, right? We're going to replace this idea of T, the true score, with something called the common variance, or the variance that the item shares with other items on the test. So again, that this scale X, test X, this is item K, and I want to know, okay, well, what part of K is likely related to the true score? So if I have multiple items that are all measuring the same thing, or intended to measure the same thing, well, that means I can assume, or at least I'm going to assume in this case, that any variability that this item shares with other items on the same scale is likely being driven by the true score. Right? The reason why this item shares variability with the other items is because they're all trying to measure the same thing, the same true score. So we can call this our common variance, or sometimes it's referred to as the communality. Okay, it's usually indicated by 8 squared. So this is the variance that this item shares with all the other items on the scale, and we're assuming that the reason why it's sharing variance with the other items is because it's all being driven by the same true score, the same thing, like depression. It's being driven by that, making those items relate to each other. Okay. And in each item, there's going to be variance that is shared between them. There's also going to be variance that's unique to that item. So instead of thinking about E as error or random noise, we could think of it as the variance that's just not shared. So there's variance shared between the items, and then there's variance that's sort of unique to an item that it doesn't share. And so you can think of that as its uniqueness or unique variance. The unique variance is made up of two different kind of variances together that we can't often pull apart. You have variance that's specific to the item, meaning that there's something about that item that there's variability that is just different for that item than for other items. And there's also good old random noise. So we got measurement error mixed together with specific error, so specific variance. And that together makes up this unique variance. Okay. So this is the part of the variance that item K shares with other items. This is the part that it doesn't share with other items. An example of this would be, again, thinking about depression. If thinking about the item like in the past 6 weeks, I've either lost or gained weight. So let's pick on that particular item. So if someone is depressed, their weight loss or gain is likely to be related to that depression. So there's some portion of variance across people that is related to other items that measure depression. However, some people just may be on a diet. Okay, so they may have lost some weight simply because they're trying to get in better shape. And they're not depressed, it has nothing to do with depression. So there's some portion of that item that has variance that's just specific to weight loss. It's specific to losing weight or getting in shape or something that's not related to depression that's going to show up in this U. And then there's also just the regular old measurement error, just the sort of noise that gets introduced in the process of measuring just about anything. Okay, so then you have those two together creating the variability on that particular item. Okay. So the common factor model, again, this is just sort of breaking it down again, just to reiterate what we've already talked about. The variance of any particular item on a scale equals to the variance that's shared, the common variance, plus the variance that's specific to that item, that's just, something about that item that's different from other items, plus random measurement error. The two of those things together are what we call the unique variance. We can't really pull them apart. We don't know how much of what is what. We're not able to really identify the differences. We know they're both in there, but they sort of end up getting lumped together. It's just a part of the item that is unique. All right, so there's a shared variance, the unique variance. We call the shared variance the communality, and the unique variance is sometimes referred to as the item's uniqueness. Okay, so again, I think it's the total variance is the common variance plus the unique variance for any item. You can see how this sort of corresponds, or at least is analogous to, that any item is composed of the true score plus error, and it just happens to be we're looking at the true score as it is driving relationships among items that are all measuring a similar concept. Okay. The common factor model assumes that the commonalities represent, and it's supposed to be a U, commonalities represent variance that is due to the concept. All right, so we're assuming that the reason why items are sharing variance is because that variability is being driven by the same factor. Right? So someone's depressed, and that's pushing them to respond to items in a similar way, which is why those items are related. If I'm high on depression, I'm going to respond higher on most of the items. If I'm lower on depression, I'll respond lower. And it's going to make the items sort of share variation across respondents, right? It's the same scale. All right, that's great. It's great that this thing does that. But how do we calculate commonalities? How do we even estimate this measure? Because it sounds a lot like Cronbach's alpha. It's a measure of sort of the common variation. But if this is something different, how do we get there? So let's think of the regression approach. If we had, something like a Y factor, something like a depression factor, we could identify, slopes of the items here, and identify intercept or something, and error. We can actually create this. We can create these measures as sort of weights or coefficients to weight each item and create a predicted score. All right, so it's a more general form. I can just sum all the slopes times all the items, add them up, add in the intercept, add in error, and I can sort of maybe predict this factor. But let's think about this a little more theoretically. Still thinking regression, so if theoretically items don't make up a factor, like I just said, the factor, the thing that we're trying to uncover, we're hypothesizing that is actually driving the responses. So if I'm looking at it this way, this looks like these items are predicting or driving the factor score, driving this thing over here. That's not what I want. Right? I want something where the factor, this unmeasurable latent variable, is actually driving the factor. Sorry, the factor is driving the items. I think I said that the same thing twice. I'm trying to uncover what latent thing is actually driving people's responses to items, right? So example, if you know someone is depressed, then you should be able to predict how they will respond to each item on the CESD. It's their depression that's actually going to predict their responses, not the other way around. So we need to flip this idea of regression sort of around. So the regression model flipped around. Let's predict the item from the factors, right? So here we have an item, K, the same one. And what I want to do is I want to identify any number of factors. It could be one factor, it could be 10 factors, whatever it is. And each of those factors are going to have a coefficient, a value that's going to relate the factor to the item. Some factors are going to have higher, these are called loadings. Some of them are going to have higher loadings. Some of them are going to have lower loadings relating that factor to an item. But we can actually figure out, well, okay, how many factors we need to predict this item, and sum them up by multiplying these together, sum them up, add in the unique variance, and I should be able to capture that item pretty well. So x sub k is the item. This psi jk represents the relationship between the factor and the item. I'm saying slope here, but it's like slope in quotes. It's really more like a correlation. What's the correlation between the factor and the item? And that's what this loading is. That's what these are called loadings. And fj is a factor, and e is that sort of error or residual. And even though we call it e, it's really u. It's the unique variance. It's the portion of the variance in item k here that isn't related to the factors. Right? So here we can see the arrows sort of going in the other direction now. So we're starting to theorize that these factors are really driving the responses to the items. That's why the arrows are going this way. So here I have 6 items, and I'm hypothesizing, theorizing that I only need one factor to really drive all these items. So something like depression as a general factor. Where on this side, I have similar 6 items, but I'm thinking it really requires 2 different factors, or one factor is driving the responses to the first 3, as separate factors driving the responses to the second set of 3 items. But again, I want to point out that the items, the regression coefficients, these psi values are going from the factor to the items, representing that I think that it is this factor that is driving the responses to those items. So this is where we get this idea of a common factor model. So the communality is a measure of how much each item is explained by the factor or factors, and therefore also a measure of how much each item is related to other items. So since we are theorizing here that the reason why the items are related is because they are all being driven by the same factor. So a communality measures at the same time how much an item relates to the factor or factors, and how much it relates to other items on the same scale. So we can actually find that by taking the commonality for any one item equals to the sum of the squared loadings for each item across the factors. So if I have multiple factors that are all sort of predicting the same item, I'm going to square those loadings for each item. I'm going to sum up all those squared loadings, and what I'm going to get is then my communality for the item in question, the one I'm looking for. Whatever's left, if you look at the total variance of an item, whatever's left after looking at the commonality then is the item's uniqueness. It's the part that isn't shared, isn't related to the factors.